Alright, here we are for the last section, conditional probability and independence. So, the learning targets for this chapter are calculating and interpreting conditional probabilities and determining if two events are independent. That's what our first video will be over. Then we'll have another video that's over the general multiplication rule to calculate probabilities, and then also for tree diagrams to model a chance process involving a sequence of outcomes. And the last video will be the multiplication rule for independent events. So, what is conditional probability? Conditional probability is when we're talking about an event happening knowing another event. So the probability that one event happens given, that's the key word, given that another event is known to have happened is called conditional probability. So this is the notation for conditional probability. This is a vertical bar. This is not a division sign. This is read the probability of B given that event A has already taken place. So here's an example. In 1912, the luxury liner Titanic, on its first voyage across the Atlantic, struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died. Suppose we randomly select one of the adult passengers from the Titanic. We're going to define the events F to be a first-class passenger, S is that they survived, and T is that they were in third class. So part A, find the probability of T given that S has occurred. So looking back up here, we're talking about the probability that a randomly selected person is in third class given that we know they have survived. So since the surviving is what was given to us, we're looking just at their survival row. So third class would be 151 of those passengers of the 442. So this probability is 0.342. The given took us away from the total. In the past sections, we've been looking at the total of the table, 1,207. But the given parameter breaks it down into one of the subtotals. Alright, so part B, given that the chosen person is not a first-class passenger, what is the probability that she or he survived? Write your answer as a probability statement using correct symbols for notation. Alright, so probability of survived given not first class. So if you're not in first class, we're looking at both the second and third class. And then when we're looking at survive, we're looking at the 94 from second class and the 151 from third class over the total from second and third class, 261 and 627. So we have a probability of 0.276. So to find conditional probability with a two-way table is quite simple because you can break it down into those subtotals. But in general, if we do not have a two-way table, we need to be able to calculate it as well. So here we have a formula. The probability of A given that event B has occurred is equal to the probability of A and B divided by the probability of just B. Notice that the given is what probability we're dividing by. Here we have it in simpler terms or notation with the intersection. Remember, if we have a Venn diagram, we're looking at the intersection there. So in other words, it's the probability that both events occur together divided by the probability of the given event. Okay, the same thing happens if you switch A and B. We're just dividing by the probability of A because A would have been the given situation. Alright, so thinking back to that Facebook and Instagram example from the last section, remember we had 68% of residents in the apartment complex used Facebook, 28% used Instagram, and 25% used both. So suppose we select a resident at random. Given that the person uses Facebook, what is the probability that he or she uses Instagram? So here we have our given probability of I, given F. So remember the probability of I given F, this should be intersection right here, not a given bar but an intersection. The probability of both was 25%, so 0.25, and the probability of just Facebook was 68%, 0.68. To the division, we get 0.368. Alright, so independence. Events A and B are independent events if knowing whether or not one event has occurred does not change the probability that the other event will happen. Okay, so in other words, the probability that event A will happen, given that B already has, or equals the probability of A given that B does not happen, which this would just be the probability of A. The complement of B would be A, if that makes sense to you. So we're just looking at whether the probability of event A given B just equals the probability of event A, meaning that secondary event, the known event, did not affect the actual outcome of the probability. And then alternatively, switching A and B, probability of B given A equals the probability of B. So we're looking back at the example of the gender and the pierced ear, and we're going to look at the probability of pierced ear given that they're a male. So pierced ear given that they're male is 19 of the 90. That's just your traditional conditional probability. Then we're looking at the probability of the pierced ear given that they're female. So you have the 84 of the 80 females. So knowing that the chosen student is male changes greatly reduces the probability that a student has pierced ear. So these two events are not independent. Here's another example. Probability about being left-handed and the gender. Is there a relationship between gender and handedness? To find out, we use Census at School's random data selector to choose a simple random sample of 100 Australian high school students who completed a survey. The two-way table summarizes the relationship between gender and dominant hand for these students. Suppose we choose one of the students in the sample at random. Are the events male and left-handed independent? Justify your answer. So we're looking at the probability that they're left-handed given that they're male. And is that the same as the probability that they're left-handed that they're female? Because female, this would be the complement of male. So male complement. Alright, so left-handed and male. So remember, the numerator is the probability of left-handed and male. So we have 7 divided by just the fact that they're male, 46. So that's 0.152. Then the probability that they're left-handed given they're female. So we look at female, they're left-handed, there are 3. And the probability of just being the female, we are 54 of them. So 3 divided by 54 equals 0.056. These are not equal, therefore male and left-handed, these two events are not independent. Knowing that the student is male had increased the probability because we went from 0.056 to 0.152.